Hello, everyone. My name is Adrian Flores Orozco, and I am going to show you some of our results regarding the application of complex conductivity for the monitoring of nanoparticles for groundwater remediation. Well, the use of nanoparticles promise a faster degradation of contaminants and in particular the ability to directly inject the degradation agent into the contaminant plume. So I'm not going to talk so much about the degradation of the contaminant, but actually going a little bit provocative and say, okay, are we sure that we are delivering our remediation agent directly to the target? Is this really working? I am going to show some results by the application of microscale zero valent iron and nanogoethite particles. So I am going to show also results where we apply complex electrical conductivity. So, okay, this is the approach. This is what we are going to use. And the changes in the electrical properties of the subsurface, the conductivity and the polarization, can inform us or can give you some information whether the particles are being properly delivered or not. There are some laboratory examples that have shown that complex conductivity is sensitive to the presence of zero valent iron. So we went to the field. The first example is our measurements collected in Belgium in an area where we have high concentrations of TCE, trichloroethane. And in the area we have a system we have two aquifers, a shallow aquifer, which a maximum depth of 4.5 meters. Then we have aqueduct, an area with low hydraulic conductivity between 4.5 and 8.5 meters, and a deeper aquifer. And this deeper, the contaminant is found also in the deeper aquifer, and this is the target of the injection. So we want to inject the nanoparticles, so we injected the nanoparticles at the depth, in the depth aquifer. We injected 21 kilograms of microscale particles, and we injected from bottom to top with 50 centimeters intervals. There were some restrictions for our collection. They told me, okay, we have 15 minutes is the time that the injection takes, and is the time that I have for the collection of data. And we have also 15 minutes to collect data in the time that they were using to place the pump in the next injection point. So I only have 15 minutes to collect the data, and we have a maximum length of 24 meters. That was the maximum length. We were this experiment took place inside of an industrial area. So we decided to go for time domain induced polarization measurements with 2 seconds pulse length. We used 24 electrodes with 1 meter separation. So one of the first challenges is the spatial and temporal constraint, how much time and how much space we have for our data collection. The measurements that we collect before the particles injection are shown now here, and they reveal clear changes in the real and imaginary component of the complex conductivity, in the conductivity and the polarization properties. And these changes are in agreement with expected variations in the lithology. We have on the top the shallow aquifer, and we are able to discriminate between the saturated and unsaturated zone. Then we have the clay-rich area, the aquiclude, and the deeper aquifer. More interesting is we see an anomaly with high polarization values, which is in agreement with the high concentrations of TC. So we say, okay, actually, our measurements are sensitive to the lithology and can detect where is the contaminated area. So we were happy with the measuring protocol. When we started repeating the measurements, again, during the injection and one repetition of measurements after finishing the injection. They started at 10.5 meters depth. And of course, we see this initial change in the conductivity, and where we were very happy. Then we collected measurements at 10 meters depth, and the changes were not so clear. Then we went at 9. Then the injection was moved to 9.5 meters depth. We start seeing some changes, but also we start seeing some variations in the shallow aquifer. That was a little bit strange. We continue the injections at 9 meters depth, 8.5 meters depth, and we keep seeing some changes in the deep aquifer, but we continue increasing the changes in the shallow aquifer. We repeated the measurements 1 day after or 12 hours after the last injection, And we actually see that the main response is in the shallow aquifer. So that was a little bit disappointing for the colleagues there. It's okay, well, probably the geophysics is not working. We look at in this polarization, and actually during the first injection, we will look at the polarization response. We see actually, if we see at the phases, the main changes are associated to the shallow aquifer. The second injection from 10 to 10 meter steps also revealed a larger variation in the shallow aquifer. Only by the injections at 9.5 meter steps, we start seeing some changes in the deep aquifer. But again, we see a large variations in the shallow aquifer on the top of the clay-rich area. So again, the colleagues there were a little bit disappointed. Yeah, maybe you are more sensitive, some problems with the contact electrodes, something in that direction. So in that moment, because they were targeting the deep aquifer, and all the information that they have was on the deep aquifer, they were not very confident with the geophysical results. When they actually start looking at the data, they say, well, we don't find the iron in the deep aquifer. So they start drilling small wells in the shallow aquifer. And actually, what they find out is that the highest iron concentrations were delivered not in the target. The higher iron concentrations were found in the shallow aquifer, exactly as predicted or as revealed by the complex conductivity. So they contacted me and said, okay, maybe you can come back with your results, because it seemed that it was actually working. And the problem was that they didn't have so many sample observation wells in the shallow aquifer, so they were not able to validate on site the results that we were obtaining with geophysics. There is something that is more interesting and that we can discuss, is that we observe that if we compare the baseline to the measurements after the 12 hours after the last injection, we see a change in the polarization response. We see actually in the deep aquifer, we see an increase in the phase in the polarization. And in the shallow aquifer, we see a decrease. And one thing is, maybe this is associated to the degradation of contaminants. But actually what we believe, or what we think is controlling this change in the response, is that on the deep aquifer, we have the bare zero valent iron, because the particles are delivered, and we inject an enzyme that consumes the coating of the particles, this kind of this dispersion material that we use to avoid the activity between particles. While in the shallow aquifers, where the enzymes were not injected, the particles are accumulating, and they still have this coating avoiding the reactions. This coating limits the polarization response, and that's why we see these changes. But it's something that we can also discuss. But actually, this is important because it shows that the complex conductivity is sensitive to the changes in real time associated to the injection of the reaction agent, and actually to the chemical changes into these particles, whether they are coated or bare. I mean, whether the coating is being consumed or not. Another example to show that, okay, maybe we don't need the polarization the whole time, is some measurements that we collected in the Czech Republic, in a site where we have Vitex contaminant, especially toluene. Here we have relatively high concentrations of toluene, and the target area was between 5 and 7 meter steps. It's a shallow aquifer. And in this time, the injection were going from top to bottom. We injected, in this case, iron oxides, which associated to a much weaker polarization response. And the aim was to inject 300 kilograms of iron, in this time dispersed by humid acids. This area is completely different. We have a high electrical conductivity, still showing some vertical variations in agreement with the datological changes, but we see a low polarization response, negligible polarization response. And also we don't expect a huge polarization at the low frequencies due to the goethite particles that we're injecting. Measurements here were performed at 1 Hertz in the frequency domain. And actually, one of the idea was, okay, we mute the response from the particles and from the subsurface. Maybe what we see is the changes associated with the transformations of the contaminants. We didn't see a change in the polarization response. And what you can see here is an animation showing the changes in the electrical conductivity at different times during the experiment. And actually, it's interesting to see that we are injecting between 5 and 7 meters depth, but actually most of the changes are again very close to the surface, between 2 and 4 meters deep. No, again, similar to the previous experiment, the response is not where we are expecting, close to the injection, but close to the surface. This was again showing that the particles were not correctly delivered. We actually had this daylighting, the particles were flowing to the surface, actually upgrading from the injection point. So in this case, we have a visual confirmation that the geophysical images are right, that we don't see the response to the particles because they were not properly injected. But if we look at the electrical response of a few pixels over the experiment, over the length of the experiment, we can see that actually the geophysical images were seeing or were revealing a change at 30 minutes after the injection. In this case, the injection were very slow to avoid fracking. However, at 30 minutes, the conductivity changes. And we believe, or we interpret this change associated to clogging. So the particles were being delivered, they were clogging next to the injection point, and we're keeping accumulating. And that's why at 140, the fracking develops and the particles are pushed into the subsurface. So actually, geophysics is, if we will have belief in or if the experiment, if we have trust in the geophysical data at that moment, maybe we could have changed our injection and say, okay, well, let's stop the injection here because something is happening in the subsurface, and let's relocate the pump in a different point. So actually, we believe that the IP is ERT, electrical resistivity, conductivity, or reduced polarization imaging. They are sensitive to changes in the pore space at the field scale associated to the injection of particles. And we believe that this information can be used to take decisions on site in real time to redesign the injection of the particles and improve the efficiency of the remediation. We believe that these observations are valid for other remediation, not only for injection of particles, maybe for other kind of in situ remediations. We can use geophysics in the same way. So electrical imaging is a powerful tool, and we believe that this information should be used on real time to adjust the remediation strategy and improve the efficiency. I right now not discussing so much the degradation of contaminants, but I think that something else that we need to take into account is that maybe we should use geophysics or geophysical results to plan the sampling accompanying the remediation. In these experiments, the geochemical sampling was pre-designed, but we believe that maybe we will be more efficient and we provide a better interpretation of results if we have performed the sampling based on the geophysical results. Well, I am looking forward to the discussion and to a number of questions. Thank you very much.